Om Shri Sairam. Welcome to the afternoon session of the last day of the Indo-US Conference 2. For this session, we have a keynote address by Dr. Mehra Aguer. Dr. Mehra Aguer is a mathematical epidemiologist working on infectious disease dynamics. With a multidisciplinary research profile, Dr. Aguer has a double European PhD degree, PhD in life sciences, and also PhD in population biology. She is a trained she's trained in dynamical systems theory, stochastic process, nonlinear dynamics, bifurcation analysis, and biostatistics. And her scientific interest addresses significant mathematical and fundamental questions in biology, medicine, with special focus on public health epidemiology modeling. Dr. Aguer is a former Marie Curie Fellow at Toronto University, Italy, and is currently the group leader of Mathematical and Theoretical Biology Group at the BASEC Center for Applied Mathematics, BCAM, in the Spain. Dr. Aguer is is the member of the Board of Directors of the European Society for Mathematical and Theoretical Biology, serving as Vice President from 2018 to 2020. As a member of the BASEC Modeling Task Force, Dr. Aguer is currently assisting the BASEC health managers and the BASEC government during the COVID-19 responses. Today, Dr. Mehra Aguer will be speaking us on the topic modeling COVID-19 in the BASEC country from introduction to control measure response. Over to Professor Mehra Aguer. Thank you.
Professor, thank you all for the organizers for this kind invitation, and there's such a nice introduction. I'm going to present today my experience with COVID-19 modeling in the Basque Country. So I should share my screen, put in
it's
full
shared.
presentation. Yes, can you see my slides?
Yes, ma'am. Perfect.
Okay, perfect. Thank you. So good morning, everybody, which are on this European region. Good afternoon for you in India and in Asia countries, and I guess it's still very late in night from people on the Americas, but anyway, I hope you are all with us. Thank you for the invitation again, and I'm going to share my experience on applications of mathematical models during the COVID pandemic. When the pandemic starts and what is going on at this moment. So, introduction, I'm super aware of what's going on at this moment. Since December 2019, there was a severe respiratory syndrome caused by a new coronavirus that was declared a pandemic by the World Health Organization already in March. And as of 3 days ago, WHO has reported more than 250 million cases with around 5 million deaths caused by coronavirus, this new coronavirus, SARS-CoV-2. It is a respiratory disease, so it's transmitted from human to human by droplets, coughing, and sneezing. There is a substantial global underestimation of the number of infections, and it makes it very difficult to control the spread of the disease because most of the cases are considered asymptomatic or mild. So everybody is at risk of acquiring the infection. And the important thing, or the important factor, is that the infection follows a hierarchical chain of risk where ages or comorbidities are at risk to develop severe symptoms of the disease. Okay, so from 2 days ago as well, 5 days ago, October 25, we can see here some information on the worldwide vaccination. So far, we have around 50% of the world population receiving vaccine, but only 3% of the people living in low-income countries have received at least one dose, which makes no sense at all in terms of pandemic control, because the pandemic is a pandemic, so all the regions of the world should have a similar amount of vaccination coverage, and that's not the case. So just to draw your attention that COVID-19 pandemic is not over yet, unless everybody is able to get the vaccine available. So good luck is that vaccines were available in a very fast and period of time. So in less than a year, we had several vaccines that were licensed for emergency use. These vaccines are very effective against severe disease. However, the so-called sterilized immunity, that when individuals which are transmitted not only develop symptoms but also stop transmission, this sterilized immunity still never away. And that's the main issue now when one wants to evaluate the impact of the vaccination rollout programs in the several countries. Okay, so at the beginning, while we do have the so-called wild type of variant, 4 vaccines were taking as a rollout in Europe, such as 2 were mRNA vaccines, Pfizer, BioNTech, and Moderna, with approximately 95% of vaccine efficacy after second dose. And we also had Oxford, AstraZeneca, and Johnson, which are viral vaccine with a bit smaller vaccine efficacy, as you can see here in these plots. So at the beginning of the year, we had information about the efficacy for the second dose for the AstraZeneca. We could reproduce these results by using the information available in this paper here, where the overall vaccine efficacy after second was approximately 70%. We had larger studies on the Pfizer-BioNTech vaccine, and they're a bit more detailed, where we can analyze the vaccine efficacy after first dose and after second dose, and also difference between vaccine efficacy against infection or hospitalizations. And we also did some exercise using the information available in this paper here. You could see that while after first dose we had short or smaller vaccine efficacy against infection, something between 50 and 60%, we had already a high vaccine efficacy against hospitalization. And after second dose, both vaccine efficacy by infection and hospitalization remained quite large. So this is information back in summer for Spain and the Basque Country. By August 22, we had approximately 7% of the overall population having at least 1 dose. Sorry, with 2 doses and more than 70% with 1 dose. This is up to date, up to October 15, and we can see here that we have now almost 80% of the population covered with 2 doses already. With different vaccines, and Pfizer is the one which is most used at the moment. Of course, in the face of the new variant of concern, in the case and this vaccine is not yet the perfect one for us. However, some fresh study just coming out recently showed that, okay, indeed, the vaccine efficacy against infection has decreased after the Delta variant was identified. However, but decreased against other variants, non-Delta as well. The important thing is that were still very high. So far, so good, at least against severe disease. Okay, so just to give a brief overview, and at the moment when the COVID-19 was declared as a pandemic in the Basque Country, a multidisciplinary task force called Basque Modeling Task Force, BMTF, was created to assist the Basque manager and the Basque government during these responses. And I was one of the researchers participating in it. Our task force had the main objective of describing the pandemic in the Basque Country in terms of disease spreading and control, to make projections to the national health system during the increase of population, going to also given the severity of the cases that were identified, at least in the first wave of the pandemic, and to monitor the disease transmission when the country lockdown was generally gradually lifted, or as we see that there was something else going on, we start to restrict again, and we were responsible to see or to give prediction on the impact of those measures. Of course, now it's important to evaluate how severe are those new waves which are being identified, and evaluate the impact of
sorry to trouble you, madam.
Yeah.
Just can you hear me, madam?
Yes, I can.
If there is any program running in your system, can you close that, madam? We are facing little bandwidth issue, the feed from you. If there is any other program running, no. So only this stream is on, right?
Yeah, okay.
Okay, okay, madam.
Shall I increase the resonance or?
Your voice is getting little garbled when you're speaking. The real time, it's little
Okay,
missing.
so can you hear me now?
Okay, madam, better.
I arrived closer from the microphone. Let's see if it's better. Okay.
Yes, madam.
Okay, so so we started with a basic modeling framework.
Yeah, now it's
called-
better. Now it's better, madam.
yeah. Okay. So we start off with our basic baseline model called SHAR model, which is not but a simple SIR model with the infected classes divided into severe and asymptomatic. We didn't consider at the time the variant of concern, only the white type, because we didn't have knowledge about that. The so-called antibody enhancement that is under discussion for disease such as dengue, for instance, given the fact that we had several variants and several patterns were discarded, and we also did not consider any reinfection, at least for the first year of the pandemic. So our SHAR model basically states for susceptible individuals, severe chronic hospitalizations individuals, asymptomatic or mild, and recovered. And of course, as information was entering, we increased the model and added new classes such as for ICU admission cases, disease cases, recovered cases, and of course, disease classes to count the new incidences. So we had the basic SHAR UCD type model with four main ingredients, two parameters, beta, baseline infection rate, that is represent the infection rate for those with have some symptoms and are hospitalizations, and the recovery were easy to be estimated from the data we had. And we end up with two parameters here, the eta, which will be the hospitalization rate, and the phi will be the scaling factor to differentiate the infectivity of those which are asymptomatic from those which are symptomatic and severely ill. So the complete framework can be seen here. So we have susceptible, infected, divided either in severe or asymptomatic. Recovered cases only work for the first wave because we had limitation of testing capacity, and all of the individuals which were test positive were those which were being hospitalized. So for that moment, the recovered case was those who discharged alive from the hospitals. The ICU cases came afterwards, and then of course the disease cases. And for all these dynamical variables, we count the new incidence using this class C for each one of the classes. The important thing on this model is that the first assumption we had is that when you are considered severely ill, you can either recover, die, or move to the ICU, giving a continuation of severity, or become asymptomatic. And that model was enough for us to describe the exponential phase. So here we have each one of the classes spotted, hospitalized, ICU admissions, disease, and recovered. We can see that for the beginning of the exponential phase, all the data matched or matched within the stochastic realizations. Here we can see the growth rate that was calculated by the data we had at hand. So for the 5 variables, we had similar growth rate, which was calculated here at this blue line. Important information that partial lockdown was implemented on 16th of March, here over here, and full lockdown was implemented after we observed that the number of cases were starting to go down. So 31st of May, 31st of March, sorry, they implemented full lockdown. However, we could see a trend of decreasing transmissibility. We had a very deep exercise using the 5 data sets to do the parameter estimation and insecurity by the likelihood functions. Statistics realizations were obtained by the GLSB algorithm, and we were very happy to see that the best parameters were exactly or close to the ones we used for our first approach, modeling approach. Sorry. After the lockdown was implemented, we saw there was a decrease in disease cases reported. So we had to include a function to mimic this control phase after the lockdown. And our first attempt was using a simple sigmoidal function that surprisingly worked very well. So here's the result after the lockdown started to be implemented. and the sigma function was introduced in the system. In blue, we have the deterministic version without any control, and in color we have the stochastic version, 100 realizations with the control. And the positive, this on disease transmission, however, realization, and that could be explained by the increase of testing capacity. So from March 22 on, tests were available all over, so more cases were identified, more than what we have assumed at the beginning of simulations. However, disease and hospitalized follow well the main of these categorizations, and the ICUs had an atypical behavior after the lockdown. So we wanted to understand what was going on. We did some studies on the momentary reproduction ratio and on the momentary growth rate, which are showing that for the positive and hospitalized, the threshold of the growth was cut around April 1st. So here from momentary reproduction, April 1st, we had already crossed the threshold, and we assume that the population transmission was under control. The same was observed when you look at the growth rates, and given the assumption we had that if you are hospitalized, you can either recover, die, or move to the ICUs, we could expect that the ICUs would follow more or less this sigmoidal function here, rather than one for the positive, for the disease, and for the recovered, which had a delay of between 8 and 10 days. However, when we look at the ICUs, we observed that it follows more the increased behavior, growth behavior for the hospitalized and ICUs rather than the diseased and hospitalized. So we had to refine our model in order to get this right. So now what we have done is that we assume that disease severity is assumed to be, as soon as you get infected, you are either hospitalized, asymptomatic, or ICU admitted. We changed the transition of the ICU here, new, that was kind of ongoing evolution of the severity case to a ratio just like we have for hospitalized. So we have a proportion of individuals that go to hospitalized, a proportion that goes to asymptomatic or mild, and from that proportion we have a new proportion that goes eventually to the ICUs. And as soon as we did that and continued with the model, we could all of a sudden describe what was going on in the ICU. So by looking at the data, by looking at the dynamic, we could adjust the model simply by changing one rate to a ratio, and we were able to describe all the important variables we had available. Note that the positive cases here were still following the upper level of these categorizations. That was because we didn't have any effect on the increase of testing capacity, but that could be well described as rapid tests were introduced, and we eventually find more asymptomatic cases than before. Of course, for that we would need to adjust the model. This is the cumulative. Also for the incidences, it looks pretty well, where we have the data in black, light blue, the model prediction or the model description, and the within the context. Okay. So that's how it looks like last summer. And we could see here that for the first wave, we had a huge amount of hospitalized in red. And that was because the testing capacity was limited. Everybody which was tested positive, most of them were hospitalized or died or went to the ICU. Of course, as testing capacity increased, we had more positive detected and less severe cases. And that was resembling the amount of testings were available. Of course, those things mean that are further refinements to introduce in the model, such as the increasing of testing capacity or detection of asymptomatic infections. Also, probably the seasonality would play a role, since it is a respiratory disease, and the human behavior changes in the summer and in the winter, so we should take into consideration as well. Other important refinement to take into consideration is the human mobility. After the lockdown was completely lifted, we could observe some so-called imported cases from humans from that region going abroad, getting infected and coming back, or somebody visiting the country which are infected, transmitting the disease and going away. And of course, these isolated outbreaks would resemble this going up and down reproduction ratio that was basically used to guide public health on restricting or relaxing control measures. Okay, so time passes by, and we could keep adjusting our modeling by just increasing the detection rate, and also adjusting for lockdown measures going down. This is for the hospitalized, and this is for the ICUs. We could see that here, that the model predictions or the model description was well within, so the data was well within the confidence in the model predictions, including for the positive cases that we have adjusted for the increase of testing capacity. And of course, although it is clearly correlated with when you test more, you find more, when you test less, you find less, or the difference was still well captured by the model for all the four variables we had in mind. Okay, but the important case was that was changing the politicians' view and the decisions taking, because as I go back here, as soon as the lockdown was lifted, we see that the so-called momentary reproduction ratio, and often called in the media, are not crosses the threshold. So implementing control measures, when it goes down, you just stop these control measures, and then it goes up again, and so on. What was causing it was not a new exponential phase, but rather this critical fluctuations caused by isolated outbreaks caused by the so-called imported cases. And that was an exercise we have done. So everybody knows that we have a simple SIR and the transmission rate is below the recovery rate, we expect to have extinction of the disease. However, when we have such a small import into the system, what was expected to be extinction became a stationarity. So this is, for example, is the SIR model with import cases, where we have the super regime, meaning that we have more people becoming recovered than people being infected, and that's the solution we have. So it's stationarity. We don't have extinction, although you have large fluctuations here above the confidence interval, which would resemble new waves eventually. The exercise also shows for the supercritical regime, we have an exponential phase, and at the critical value, we want what model pandemic, where we have to go towards below the epidemic threshold, you would have observed a linear increase of cases. And clearly, that was not the case for the severe cases in the Basque Country, where we had continuation of endemic or constant number of severe cases for hospitalizations, for disease, and for the ICUs, rather than new exponential phases. So that means that while people were talking about new waves, what we had was more isolated outbreaks, and eventually another isolated outbreak that sometimes it clustered and became a very large isolated outbreaks that up the momentary reproduction ratio. However, the community control would be still below the threshold. And that was observed not only for Spain, but also for Belgium, Netherlands, and many other countries in Europe. Here, just to illustrate the difference between the first wave and the second wave on severe cases, we had the stationarity of severe cases for all of these countries going on. So, in fact, the new waves were not new waves coming from an exponential growth of the disease, but rather from isolated outbreaks that without control eventually clustered and increased. Okay, so learning about the system, we were able to identify issues that need to be considered, especially when the vaccine became available. And the first question for us was, how would be the role, the difference between the mild and asymptomatic cases versus the ones which are hospitalized and isolated? And we have developed two different models for the vaccine. Again, we use the SHAR model as a baseline, and now we have not only the susceptible, but we have the individuals which are vaccinated. Two vaccines are evaluated. The vaccine two are the one which has efficacy against infection and disease. So the susceptible individuals move immediately to the recovered class with the vaccine efficacy R. However, the vaccine one, we cut the efficacy to be only against disease. So which means that those individuals are not going to hospital, so vaccinated individuals are not going to hospital, so they are protected against hospitalization against with vaccine efficacy R. However, they are moved or they are pushed to the class of asymptomatic. So they can be still infected, they can still transmit, and only then after hospitalized or recovering from the infection they become recovered. And we could compare the results for vaccine 1 and vaccine 2 with the scenario with no vaccine. So this is the test case where we have 20% vaccine coverage and 70% vaccine efficacy, so a mild or intermediate vaccine efficacy. And for the case of vaccine 1, which protects only against infection, we see no difference or visible difference for this intermediate coverage and efficacy of having vaccine or not. Of course, the vaccine 2 would be preferable, but we have a huge impact already in this beginning of rollout vaccination. Of course, we could observe that is because it depends on what is the contribution of asymptomatic individuals into that population, which is described by this parameter 5. So we have investigated the reduction of hospitalizations by changing the transmission factor of the asymptomatic being below or above the baseline transmission rate of severe cases. And we had a very interesting result. So we plotted the result here for vaccine 1 and 2. Vaccine 1 is in purple and vaccine 2 is in green. And we have checked for different vaccine efficacies and different vaccination coverages. And what we see here is that when individuals which are considered asymptomatic transmit much less than individuals which are asymptomatic, and that could be eventually justified by not coughing or not sniffing as much as those which are symptomatic. Independent of the vaccination coverage we have, both vaccines would do well. Okay, so you would have elimination of the disease for vaccine efficacy with 100% and 100% of the population completely covered, and the reduction would be very large, for instance, for the vaccine.
Madam, we are almost around 26 minutes of the talk.
Yeah,
Madam.
I'm about to finish.
Yes. Gentle reminder.
Oh, thank you. And however, when you increase the transition rate of the asymptomatic in comparison to the symptomatic, here for 5 larger than 1, we see that only vaccine 2 is able to reduce the hospitalization fast, and vaccine 1 would never be able to stop the transmission of the disease overall in that population. The same was shown for the overall infection. That means that not only also individuals which are mild infected, when we consider the asymptomatic pain less or transmit less the disease than the CPS, we have a very small decrease observed only against infection, and the subtype decrease for vaccine, the use of vaccine 2. But when we assume that individuals which are mobile asymptomatic transmit more, we have rather an increase of number of infections overall. This is the findings here for the vaccine which protects against infection for different vaccination coverages and different assumptions of the asymptomatic contribution to the course of infection. For this case, vaccine 2, there is always a positive impact, either for a reduction of hospitalizations or overall reduction, although it's quite small. However, when we look at the vaccine disease, we have indeed a small reduction of hospitalizations for those intermediate vaccination coverage and any value assumed for the asymptomatic transmission, but we have a negative impact for the overall infections when individuals here are assumed not to transmit more than the symptomatic. And that was, in fact, being observed in Europe in the last couple of months. Okay, so this is just to show that the final result we have for this basic model, assuming the epidemiological scenario we have in the Basque Country at this moment, and the vaccination coverage. We have the first exercise used the vaccine efficacy for the Pfizer BioNTech, which were mostly used in the Basque Country by the month of the June. And here we compare the baseline hospitalization numbers over time, where we got the first result in May. In black was the epidemiological data, and in red was our prediction. And by June already, if new variants would not have been identified, we would be reaching enough impact expected by our model. We have a lot of studies going on, but I'm not going to delay anymore. You are free to contact me. I would like to acknowledge my collaborators, not only the MDB group, but also people from public health and the government, also the MDF task force. And thank you for listening. I'm happy to answer any question you might have. Thank you.
Thank you, madam,
Hello?
for your yeah. Can you hear me, madam?
Yeah.
Yeah. Thank you, madam, for your interesting and insightful talk. Are there any questions from the participants? Looks like there are no questions, madam, from the participants.
Okay.
So on behalf of the organizing committee, Dr. Anuj Kumar Mumbai and myself, I thank you for accepting our invitation and delivering the keynote address, madam.
Thank you. Thank you very much. It was a pleasure.
Yes, madam. We'll surely keep in touch for further collaboration. Thank you, madam.
Thank you. Goodbye.
So moving ahead, yes, bye, madam. Bye. So moving ahead for the next paper presentation session, next we have a paper presentation session. The session will be chaired by Dr. Surabhi Pandey. Dr. Surabhi Pandey is associated with Public Health Foundation of India from long. So she has worked as a research scientist at Public Health Foundation of India from 2014 to 2021. Then later in 2020 to 2021, she has been an exec faculty at PHFI. Then now she has moved on to Indian Institute of Public Health. She has been working there as an associate professor. Over to Dr. Surabhi Pandey for chairing the session. Dr. Surabhi Pandey.
Thank you, Dr. Vamsi, for your warm welcome. So we will be starting our afternoon session. We have three participants, Mr. Nabakumar Goswami, Dr. Puddhi, and Dr. Ghoshal. So it seems that Dr. Ghoshal is ready for his presentation. So he will be talking about the computational modeling using a novel continuum approach coupled with pins to understand the spread of infection in enclosed spaces. Dr. Ghoshal is from BITS Pilani. Dr. Ghoshal, over to you. So please start your presentation.
Good evening. Good evening. Am I being clearly audible?
Yes, perfectly audible, Dr. Ghoshal.
All right. Let me share the screen. Thank you very much, Dr. Pandey. Give me a second to set stuff up. Okay. Okay. Once again, let me ask. Am I being very clearly audible as well as you can see the screen? Please confirm.
Yes, you're audible, completely audible, and your screen is also visible. Perfect.
All right. So a very good afternoon to all of you, and thank you very much for accepting and providing me an invitation to join in here. So this work is basically based on our computational modeling approach using a novel continuum technique coupled with physics-informed neural networks to understand the infection spreading in enclosed spaces. The emphasis on enclosed spaces and the usage of physics-informed neural networks. So even before we go to the concepts of physics-informed neural networks, I would like to say exactly how do we are dealing with the infection spreading. And infection spreading, by the way, is only one of the forms in this proposal. It can be extended to several other examples. If time permits, I'll talk about it. As of now, let me consider a standard SIR model, the susceptible, infected as well as recovered group people, which already there is an existing SIR models, which are completely a set of ordinary differential equations. And in all of these forms, it's always considered that the total number of population is not changing. And also, the effective rates, the number of people there's no such concept of a concentration. The interaction between these groups can be tackled in different ways. There are certain assumptions, like it's always a homogeneous distribution of population, which is not the case in reality. So we wanted to develop this approach where there is an interaction between the susceptible and the infected people, and that leads rise to a different new pool of people. So these different pools of people can be considered very much like a gaseous mixing. So there are 3 different groups of people, and they are slowly moving into each other, and they're interacting amongst each other. And while interacting, there is a radius of influence attached to every single particular person. So this radius of influence can be taken into account in a stochastic framework as well as in a purely PDE approach. Let us not go into the stochastic approach at this phase, but let us lay down the basic fundamentals of how we are approaching this problem. Our modification is by taking into account the interaction behavior. So let me focus on the word interaction. And the moment there is a concept of an interaction of different groups of people, there is a new pool which keeps on getting generated. So this generation of new pool basically can be dependent on an activation energy, just the way of few kinetic or dynamic systems interact amongst each other. And we propose, in place of just a population number, we propose a population density. So this is a density of the susceptible people, this is a density of our concentration of infected people and concentration of recovered people. And this is the first time we are proposing a partial differential equation approach, because all of these variables are functions of location as well as time. So all the persons are moving. Let's say we are talking about enclosed spaces. Now this can be a small scale enclosure, it can be a very large scale enclosure. An example for a small scale enclosure is pretty much like an airport, or even an university campus is the best example to take. An university campus is more or less isolated in most of the cases from the rest of the world. So the people who are interacting amongst each other, that can be more or less tracked in a certain different manner. Whereas if the boundaries are completely diluted, if it's an open campus, then the way of interacting and spreading of an infection is fundamentally very different. The dynamics are very different. So we categorize these problems under we propose to categorize these problems under different activation energies, because here the activation energies are typically considered to be low, because it's not only a touch-based infection. There can be problems where even if somebody is within a close proximity of people, there is an infection can spread because of the air wind flow. So this is the first time we are developing a computational fluid dynamics model as well as a concentration dependent model being applied to SIR models or even ACIR models at a later point of time. As of now, if we, after a few basic initial derivations, this is what our problem formulation does look like. There is a time derivative. All I want you to know, there is a time derivative of the concentrations. There is a velocity, and these velocity terms practically mean how the people are moving inside a particular location. If you know, we are talking about an employee, a very classical standard employee in an academic institution. The way this particular person keeps on moving on a scale of 24 hours a day can give us a basic estimate of the velocity components. There is a diffusion coefficient. This diffusion means I'm referring back to the previous image. Every single group of people are interacting and they are slowly diffusing. The red diffuses into both the blue and the black. The black diffuses both into the red and into the blue. So there is an interaction or diffusion terms which needs to be taken into account. At the same time, because we're talking about an interaction, there is a kinetics involved here, which very much looks like a chemical reaction. Although it's not a reaction, it's an interaction. And the only reason for after writing up this particular form, it shows like a very similar to a multi-phase, multi-component flow form through porous media. And because one of the areas of expertise is on flow through porous medium, we extended this idea to a porous medium concept, whereas in ground reality, if we talk about porous media applications, there is a concept of a porosity, the ratio of the empty space divided by the overall volume, overall space. Now, how do we define a concept of a porosity as we're talking about a group of population within a closed boundary? The porosity here will be considered to be a percentage of uninfected people and not on a global basis. So this will have a scalar local variation, and it will be a function of location and time as well, once again. So this means this is the standard approach for a multi-phase, multi-component. Alpha stands for a phase, K stands for a component. The same three phases, once again, think of those three circles interacting with each other. Every single identified unique circle is a phase. At the same time, that same blue dot can be considered to be an infiltrating component when you are talking about a different phase. So there is a phase-to-phase or phase component interaction which is taken into account. And after a bit more of derivations, this is let me just give you a picture. This is where we are talking about the radius of influence. And in addition to the radius of influence, let's say these are all the people, not just people. These are different small pockets of people, okay? And every single such pockets of people may have different influence, radius of influence. And their way of affecting their surrounding is very different. So this is a classical problem of a sensitivity matrix analysis. And this means if there is a new influx of uninfected people enter a computational domain or a certain boundary as we specify, and the flowing out mixture will be a mixture of the recovered, uninfected, and infected people. And while this process is happening, this interaction can be stochastic in nature, but as of now, we are not once again talking about it. But what we are implementing is a concept of a saturation infection. Let's say you are in the university right now, so all of us can relate to it very clearly. The moment we say there is a one infection, one guy has been reported to be affected, we don't really pay that much of attention on that. We don't pay that much of heed. The moment we see, hey, this number is increasing like massively, we immediately start taking it seriously. That means we have a tolerance limit. So this is a saturation infection, we say. So the easiest way to spot out a particular way the infection is spreading, if we are aware of a saturation level of infection, that's an acceptable percentage of the effect. So this will be predefined as the simulation will run as we develop the codes. And this will dictate how does the infection actually does affect. Because people take preventive measures of closing down, shutting down, making sure interactions are minimized. So how does these kind of effects also interact or affect the process? At the same time, we are also talking about implementing a random walk particle tracking, because all of this small set of groups consists of small number of people, and everyone is moving, and their movement is pretty much randomized. Although we think we are moving from house to the office and office to the house, we also go in different directions. We are not necessarily all the time exactly one way. So we keep on changing our mind. So there is a randomness involved in the system. So I'm involving a random walk particle tracking approach here, where let's say P is the location of a particular particle or a person at a t plus delta t at a new time. It varies from the old time, the location at an old time, plus there is a velocity vector, which is an advective vector, plus there is a diffusive tensor. So, and that dictates, so there is a diffusion, there is an advection. It's an advection diffusion application. At the same time, there is a randomness involved. This delta t is basically it's a Dirac delta function. At the same time, this can be even considered, this will be replaced by a set of random numbers. So there is a randomization which will be taken into account. And if we do that, this is what we have arrived at this particular point, because most of the, not only most, I think all of the existing SIR models, ACR models, they have a dependence on spatial homogeneity. And we are saying that our approach is, we are trying to talk about a spatially inhomogeneous approximation. And for that problem, this is a generalized form of a statistical description. If we assign a certain kind of a probability to a subgroup of people to be affected or get infected. So this is a population balance approach, and it signifies the following. There is a time derivative, there is a space derivative, there is a summation component for all different forms. It takes into account the diffusivity or diffusion coefficients. It takes into account primary nucleation rate, or the primary points of identified points of infection spreading. At the same time, there can be certain cases of secondary nucleation rate. This is also we are taking into account. And secondary nucleation rate can be also thought like a trigger if we extend this work to problems not only limited to not only limited to infection spreading, but also to problems of depression kind of problems, addiction related problems. So that very different variants of that similar kind of a problem can be tackled. But fundamentally, all we need is a concept of a nucleation rate or a trigger kind of a problem. And here does lie the challenge. What is the challenge? We are talking, this is a statistical form, this is a statistical form that we are considering. What if we consider the probability that a certain number of people will get affected, and that will depend itself on the location vectors, nucleation rates, blah, blah, and so several other parameters. What is the fundamental problem? The problem is, for a normal fluid mechanical application, or even not even several other problems, we more or less assume or define a very well-posed boundary conditions and initial conditions. Here the problem is, we don't know when or where we a small population die. So we are talking about the life expectancy of a particular group of people, because recovered number of people is taken into account. Also the number of people who are dying will affect the overall population growth rate at that particular point. So here, because the boundary conditions are not necessarily very specified in all of the cases, we propose to bring in the concept of PINN, or the physics informed neural networks. And let me explain, what does it basically do? So considering us, we are referring to one of the very standard works which very recently published. And this, let's say this is what it does. Let's talk about a very simplistic flow problem, a simplistic flow problem of a blood through a human artery. And this is what they have done. And we are referring to this particular work because this is what exactly we are implementing in our work as well. All they have done to show how does PINN work. Let's say Navier-Stokes form tells you a momentum balance of a flow. There is a continuity or mass balance of a flow. At the same time, there is a well-posed boundary condition that there is a certain boundary value at a certain, it can be zero, it can be a different specific conditions, it can be a Dirichlet boundary condition, it can be a Neumann boundary condition over a specified boundary. However, if the boundary conditions were not specified, but we can think of a few errors, we estimate this particular physical problems, because our differential equation is not this. Our differential equation is the one you are seeing on the screen here. So our equation is fundamentally totally different. However, if for a similar equation, we can get an error for the physics, it's called L-phys. The error of the physics is this, more or less, this is the L-physics we obtain from Navier-Stokes equation. For our problem, we'll have a different kind of an error. Similarly, by estimating or based on some available very small number of data set points for complex boundary conditions, complex boundaries, enclosed boundaries, we can have an error because of the boundary conditions. At the same time, the data...
Dr. Kushal, sorry to interrupt you. 20 minutes are about to be there.
I'll be finishing very soon. Okay.
So yes, so you have next 2
right.
minutes, please.
Okay, thank you. So this is where the overall error is calculated, and this is minimized. And let me show you one simple result. Just look at this particular problem. This was a problem where a computational fluid dynamics analytical model was approximated. This is a simulation result. Okay, for a simulation result, there is a because of the space diameter and so on, one of the computational fluid dynamics solution, which is a standard codes available. It's a very standard problem, easy problem. There was a solution where the boundary conditions were specified, whereas physics informed neural network more or less obtained exactly the similar results where the boundary conditions were not specified at all. It only took a few basic data. So that's exactly going to be our approach. And with this approach, we hope the scope and extension of this work will include developing an ML model for data processing and classification to develop profiles for also not only for infection spreading, but also for addiction problems. In Indian background specifically, we can think of how to minimize depression as well as tobacco smoking stuff like that in very upcoming young population. There can be also problems of development of a data logger, pretty much like a watch that you wear, a smart watch, which will keep on recording your heart rates and so on, from which you can try to make some statistical correlation and come up with very predictive model. So our overall objective is not only to study to infection spreading, but to come up with a very generalistic statistical predictive tool which can solve a very wide range of problems. And we are trying to think about specific problems pertaining to Indian background, Indian scenario. So this is where I'd like to end the questions. If we, in my statement, if you have any questions, I'd be very glad to answer. Thank you very much.
Thank you, Dr. Ghoshal. This was a very interesting talk where you have taken up the fluid dynamics into the disease modeling, the TensorFlow into the disease modeling, and you have also spoken about the comorbidities, how to include them in the model. Also about the depression, which is not an infectious disease, and it's a great challenge from public health point of view. So you have given a lot of food for thought for the disease modeling, and yes, I think this may have given to the audience different kind of approach that can be included, and to consider the factors like comorbidities. Also, we can now take up the disease modeling into the area like depression. So thank you very much for your wonderful talk. We do not have any questions. So I guess your talk was really wonderful. Thank you very much. Let's move to next participant, Dr. Nagaseshu, who is from Kalam Institute of Health Technology, Andhra Pradesh. Dr. Nagaseshu will be speaking on health technology assessment on neonatal CPAP, a systematic review, meta-analysis, and economic evaluation. Dr. Nagaseshu, over to you.
Okay, thank you, ma'am. This is Dr. Nagaseshu, working as a scientist in Kalam Institute of Health Technology. Today, I'm going to present a health technology assessment on neonatal CPAP, systematic review, meta-analysis, and economic evaluation. This study was conducted in Kalam Institute of Health Technology, and our team has HTA team is Dr. Kavita Kachru, Dr. Nagaseshu, myself, Mr. Kirtan, Grishma Gopalan, and Dr. Jitendra Sharma. The content of the study includes introduction, disease burden, clinical effectiveness, as well as economic evaluation. Coming to the introduction, we are focused on the neonatal CPAP, which is essential for the neonatal intensive care unit, and present an estimated neonatal deaths is about 2.9 million occurring in every year, the majority of which happen in developing countries. And the major disease burden is taking in prematurity, it is 34%, intrapartum related conditions 25%, and infections including pneumonia, this 22%. Several respiratory diseases is a serious complication which is common to these three main causes of neonatal death. CPAP is our only intervention which has potential to be implemented on large scale in LMICs as simple and safe, inexpensive CPAP devices has been developed recently. Coming to the clinical effectiveness, our aim is to identify the effectiveness of neonatal CPAP by diagnosing respiratory issues in neonates. Objectives are reducing mortality rates in neonates, length of stay in hospital, and other complications which we are compared with standard of care. Coming to the population which we have selected is COVID-19 is the major one, the pneumonia, sepsis, necrotizing infections, pneumothorax, bronchopulmonary diseases, respiratory distress syndrome, and other comorbidities. Intervention for this study is neonatal CPAP, and comparator is standard of care. Outcomes are mortality, length of stay, respiratory support, intubation, and extubation. This is the PRISMA flowchart. We have taken from many databases like PubMed, Google Scholar, and Cochrane. And these are the studies. After extraction of the studies, duplicates, and we are screened based on titles and abstracts. Full text articles are screened. And then finally, we have selected 15 systematic and meta-analysis are included in the study. The study characteristics of this intervention is neonates suffering with respiratory failure, pneumonia, sepsis, necrotizing infections, pneumothorax, bronchopulmonary distress, respiratory distress syndrome, and COVID-19. We have performed a sensitivity analysis. From that sensitivity analysis, we have taken 60 studies from, we have plotted forest plots for seeing various outcomes like mortality, length of stay, extubation, intubation, and respiratory support. These are the different forest plot for mortality with including subgroups. So the neonatal patients out of 11,099 participants, 3,247 were treated with CPAP and remaining was treated with standard of care with a risk ratio of 0.79, and it was reducing mortality. CPAP was reducing intervention was CPAP, that is intervention was reducing mortality by 21% as compared to the standard of care. So in the same way, second outcome is length of stay. We performed forest plot, and it was reducing length of stay at a mean difference of 0 with a statistical significant effect favoring CPAP. And another outcome is extubation. Same with the intervention, CPAP, and standard of care, and it is showing extubation rate at 5% as compared to the standard of care. And last is the last but second is intubation. The meta-analysis therefore showed intubation by reducing 11% as compared to standard of care. And last outcome is respiratory support. This meta-analysis therefore showed CPAP providing respiratory support by 19% as compared to the standard of care. And the clinical cost effectiveness will be proceeded by Mr. Keertan, who is my colleague. Keertan, over to you.
Good afternoon, everyone. So, as my colleague Dr. Nagaseshu presented the clinical effectiveness of CPAP, so I'll be presenting the cost effectiveness of CPAP device with HFNC in providing ventilatory support for neonates in India. So this is the introduction. So CPAP with HFNC has been shown excellent in clinical effectiveness as presented by my colleague. Delivery of CPAP with HFNC involves more resources than the standard of care. In order to overcome this issue, an economic evaluation was performed to determine the cost effectiveness of CPAP with HFNC. Objectives of economic evaluation study was to study the cost effectiveness of CPAP with HFNC compared with the standard of care. So the standard of care here in the economic evaluation was invasive mechanical ventilation to identify most cost-effective ventilation support for Indian neonates. So the PICO components, which are population, intervention, comparator, and outcome. So population is Indian neonates with acute respiratory failure. Intervention is CPAP with HFNC. Comparator used here is invasive mechanical ventilation, which is standard of care. Outcomes, incremental cost, incremental quality, incremental cost effectiveness ratio. So coming to the methods, cost effectiveness analysis. Cost effectiveness analysis was done to study the cost effectiveness of CPAP with HFNC in Indian neonates compared to standard of care. So this model consists of two submodels, which is deterministic and probabilistic Markov, with a cohort of 1,000 neonates. And the perspective was a societal perspective with lifetime horizon. So the parameters used here were directly derived from published literature review and also primary data. So this is the structure of Markov model. So there is a possibility of healthy neonate dying naturally, or the healthy neonate having ARF and then being hospitalized, and after that he dying with the disease. So health outcomes and cost. The published literatures were used when possible, and when we don't get the published data, we use primary data or we directly contact the study experts. In this model, we have considered cost of hospitalization, physician consultation fees, medications, test, cost of device, accommodation, time loss from work of patient as parents take care of the children, which are the neonates. For conversion of foreign currency to INR, we have used foreign exchange rates, and local costs were adjusted using local inflation rates. Incremental cost, incremental effectiveness were calculated, and the formula for calculating incremental cost effectiveness ratio is cost of CPAP minus cost of standard of care divided by effectiveness of CPAP minus effectiveness of standard of care. So the results show that cost effectiveness analysis consists of two models. One is deterministic and the other is probabilistic, as I told you. From the deterministic model, the total cost incurred when the patient uses CPAP with HFNC is around 2 lakhs with the additional quality gain of 4.08, whereas the total cost of standard of care is 2.4 lakhs with quality gain 3.16, which is low compared to that of CPAP with HFNC. Incremental cost was minus 34,800 with the incremental quality of 0.9. Base case ICER is minus 37.639. So these are the results from probabilistic model, which is ICER scatter plot. As you can see, most of the data falls under first and fourth quadrant, which is near to the base case ICER. So the base case ICER was somewhere around minus 37,000 with the 0.9 as quali. So if the ICER is negative, we still can accept the medical device or the drug or any treatment or any programs. It does not mean that you reject the particular device or particular program just because it's negative. In the end, all you need to get is you need to save cost and you need to gain better health. So 1000 iterations were performed to deal with uncertainty. The ISO value obtained from PSA are very close to the base case ISO. This is a cost effectiveness acceptability curve with respect to willingness to pay. So the willingness to pay, when the willingness to pay is somewhere around 50,000, you can see the probability of CPAP with HFNC being 100% cost effective, and the net monetary benefit for CPAP is around 6 lakh, and for invasive mechanical ventilation it's around 4 lakhs. The incremental net monetary benefits is calculated to be 2.3 lakhs. So from the discussion, the main result of the study was that CPAP with HFNC was cost effective. As per ICES Catalprot, HFNC is less costly compared to that of standard of care, with outcomes being high. Negative ICER implicates that the intervention is less costly than the comparator. Since the incremental net monetary benefit is positive, CPAP with HFNC is cost effective. The conclusion in the systematic review, we found administration of CPAP is effective, and it also reduces mortality rate and length of stay. Incremental net monetary benefit is again positive, cost effectiveness. So CPAP is cost effective ventilator support, and also a budget impact analysis can be performed to give the government a better idea of resource allocation. So these are the reference, and yep, we are done with our presentation.
Uh, Thank you, Dr. Nagaseshu and Kirtan, for your wonderful presentation. I have a few questions. So you said that from the systematic review, you found that CPAP is uh, really a better device than the usual your intensive care ICU's ventilators for neonates. So, was there any quantification of that? How much mortality, as you have spoken, mortality and the stay in length of stay in hospital was reduced by using CPAP. So, what was the by what proportion mortality rate was reduced, and what was the length of hospital stay when CPAP was used in comparison to the other?
From the literature of secondary literature which is available, we have collected the data. So based on those sample sizes and population, we have selected, and based on those results only, we have plotted the forest plots. So overall subgroup analysis and the subgroup analysis showing that mortality rate was decreasing when compared to standard of care, as well as length of stay is also reduced when compared to standard of care. This is a secondary literature which is available already. That means we are comparing with the standard of care to show how the CPAP is more effective than compared to the standard of care with less cost effective.
Right. So my question was to what was the length of a stay when CPAP is used? So you said that with the CPAP, the length of a stay is reduced in hospital. So can you elaborate on that?
Yes, suppose neonates staying, suppose we are using standard of care, the neonates are staying for 15 days or
Yeah.
20 days. By using the CPAP, they can reduce like for 1 week or 4 days based on the disease condition as well
Yeah.
as severity condition of the neonates. So we can reduce the length of stay of neonates so that the cost of expenditure is also less, and the baby
Okay.
will not suffer from the disease also. They won't suffer a lot by using this intervention like neonate CPAP.
Right. Mr. Keaton, I have a question to you as well. You have the economic evaluation of CPAP, and this is a really wonderful study. I would be very much interested to understand. You said it is cost effective in comparison to the other standard of care instruments. So, what in your study you found that how cost effective it is? Can you quantify it? I mean, like this. I mean, how much cost effective CPAP is
Ma'am,
when you compare it with the standard? Yeah.
okay, I'll just show you one slide where I specified that it is cost effective. Ma'am, from the results, so again we have two models in this. One is the deterministic, and one more is the probabilistic model. The deterministic model is nothing but the basic model. So
Okay.
here we got to know that the CPAP cost for length of stay of 7 days
Hmm.
is said to be 2 lakhs with
Okay.
quali of 4.08. Quali is nothing but quality adjusted life years gained.
Yeah. Yeah.
And next, when it comes to standard of care, for same
Hmm.
7 days, we have found out that the cost is 2.4 lakhs and the quali gained is 3.6. So here the quali gained is very low, but the cost is very high.
Hmm.
But when you
Okay.
when you when you go through CPAP with HFNC, the cost is a bit low,
Hmm.
which gives you better outcome.
Right. Right. So nearly we are saving around 50,000 per case, as well as we are increasing the chance of the better quality.
Yes, yes,
Yeah.
yes,
Okay.
yes,
Yeah.
ma'am. Yes, exactly.
Okay. Thank you very much, Dr. Nagaseshu and Kirtan, for a wonderful presentation. Uh, I hope the participants and the audience have enjoyed, and this was different from the modeling perspective. But I'm sure this has given everyone another outlook towards the public health. So, thank you very much, both of you. We move to the next uh, presenter, Dr. Naba Goswami. Dr. Naba
Yeah,
will be yeah. Dr. Naba will
yeah,
be speaking on effect of awareness programs by media on the COVID-19 outbreaks, a mathematical model. You, Dr. Naba.
yeah. Thank you very much. I'm Nava Kumar Goswami, senior faculty member of Time Tirupati Institute of Management Education. Basically, it is known as Time Private Limited. So I did my PhD recently from Mysore University. So the topic is effect of awareness program by media on COVID-19 outbreaks, a mathematical model. Completely we solve mathematically mostly here. So mathematical modeling is a process of representing real world problem in mathematical terms in an attempt to find the solution of problem. A mathematical model can consider as a simplification or abstraction of complex real world problem or situation into the mathematical form. Mathematical model makes an important contribution in terms of developing problem solving skill of student. Also modeling emphasize mathematical relation and ensuring of students to develop their learning style and understanding of mathematics. Mathematical model gives us better education how to live in the society with disease. So fact of COVID-19 disease. COVID-19 is caused by infection with the SARS CoV-2, which is transmitted to human through breath in air contaminated by droplets and small airborne particles containing the virus. COVID-19 belongs to coronavirus family, which also include SARS virus and MERS virus. The family of coronavirus includes that causes of common cold and flu. The first case of COVID-19 was recorded on 17th November 2019 in China. The COVID vaccine can help prevent new variants from emerging, but doesn't protect 100%. So that means we should take care of us. Presently, worldwide, more than 24.6 million people infected cases has been reported and across 223 territories, which is more than 22.3 million infected cases are recovered, and more than 4.9 million infected cases has been died. So in India, the first COVID-19 new novel corona case was reported 30th January 2020 in the state of Kerala. Presently in India, 3.4 million infected cases has been reported across 32 states, while 3.3 million infected cases were recorded and 4,57,222 infected cases has been died till now. So our model, the mathematical model is divided 7 different compartments according to the nature of the disease. Susceptible human population, exposed human population, quarantine human population, asymptomatic human population, symptomatic human population, medical care individuals, and recovered. So here a mathematical model will form for COVID-19 is proposed by considering media as an incident term. As media can reduce the transmission, so we have incorporate media impact for human population by including the factor b e to the power minus m is. Is means our symptomatic human population in the incident term corresponding to human transmission. This is our flow of the flow diagram of the model. Susceptible becomes exposed. There are 3 compartments we consider: quarantine, symptomatic, asymptomatic, and the medical care, and then recover. How we consider is a C. In this formulation of model, our main focus is on media awareness program, infected human population, symptomatic and symptomatic, and quarantine without medical care as well as with medical care. So considering 2 population in variation and total population in varying and homogeneously mixed, all people are equally likely to be infected by the infectious individual, and if they come into the contact. The susceptible individual by the infected individual if they came to contact. The susceptible individual after being exposed to the COVID-19 infection can progress to quarantine. And infected means asymptomatic and asymptomatic classes with different transmission rate. As media can reduce the transmission, so we have incorporated media factor, so e to the power minus m is as incident term. Here we assume the quarantine population are exposed into the will start showing symptoms and then move to the medical care compartment for the isolation and treatment. The asymptomatic individual are progressed by the proportion sigma, and while exposed to coronavirus, but common symptoms have not yet been seen. The symptomatic individual exposed by 1 minus sigma, here we saw, and becomes symptomatic class after showing symptoms of the coronavirus by exposed individual. This individual who have been developed by serious clinical symptoms or critical illness been isolated from for the medical care. So those people are medical care isolated. Subsequently, due to the proper medical care, individual may recover and move to the recovery class with gamma 2. And similarly, individual who are asymptomatic individual or moderately sick can join recovery class at the rate of gamma 1, and quarantine individual also progress to recovery class at the rate of gamma 3. The awareness program by social media such as newspaper, magazine, television, and radio can play an effective role of transmission of the disease at the initial stage of emerging. Not at the infection disease, not at the initial stage, at the time of the vaccination drive also. So the media play the effective roles. That is also we include here. The susceptible individual respond to a disease through the mass media based on risks, that is gaining largely through infection through the mass media. Therefore, we modify the transmission rate beta, initial transmission rate you consider as beta, to beta e to the power minus MIS is the contact and transmission term. It measures the susceptible spreading the virus for the infection of the susceptible individual, where e to the power minus MIS is a function of average number of new reports of IS, and M is the positive constant which represent the weight of weight of impact of media coverage. Now normally e to the power minus MIS is a decreasing function of IS. So, which states the number of news reports increases, susceptible individual will maintain the disease prevention, such as wearing mask, social distancing, washing hand, etc. And the result decrease the contact transmission rate of disease. So, if m equal to 0, so that means if we consider m equal to 0, then the transmission rate of the disease is a constant. Generally, contact transmission rate of the disease is not only potential to the spread of the virus, but also strongly connected to the awareness to the disease is susceptible of the inhabitants. Hence, we assume that the variable m is greater than 0 to manifest the impact of media coverage to the contact of transmission of the disease. So, based on above assumption, we lead the mathematical model as proposed. So here, biological representation of the parameters. So recruitment rate of human population, B is rate of transmission, symptomatic individual, B1 is asymptomatic individual, B2 is quarantine individual. Xi1, Xi2 are the progress from exposed to quarantine, and Xi2 is exposed to infected. Infected means there are two classes, one is symptomatic and one is asymptomatic. Sigma, the fraction of exposed individual progress symptomatic infectious class. 1 minus sigma, fraction of exposed individual progress to IS. Delta is the rate of progress. Delta is the rate of progress asymptomatic to symptomatic. So next, row 1, row 2, row 3 are the rate of detection of isolation, asymptomatic, symptomatic, and quarantine. So here, those are detection, sigma, row 1, row 2, row 3. So next is gamma 1, gamma 2, gamma 3 are the, gamma 1 is the recovery rate of asymptomatic, gamma 2 is recovery rate of medical care. Since we consider such a way, symptomatic becomes the medical care, everyone goes to the medical care, that means from they will recover from there. And gamma 3 recovery of quarantine infected individual. Mu is normal mortality rate, D1 disease related mortality rate, D2 is disease related. Another mortality rate, M is the positive constant. The disease-free equilibrium and basic reproduction number we calculate. This is our disease-free equilibrium point. So in that disease dies. We find the basic reproduction number R naught by the next generation matrix method. This is our reproduction number. The quantity R naught is known as basic reproduction number. The expected number of secondary classes produced in completely susceptible population by the type of infective individual of the system. So existence of endemic equilibrium point, we calculate all endemic equilibrium point, then we prove the local stability of disease-free equilibrium. If R naught is less than 1, the disease-free equilibrium E naught is locally asymptotically stable, otherwise unstable. The Jacobian of the system disease-free equilibrium point, so E naught is obtained. This is our Jacobian matrix, and clearly from the matrix we can observe that two eigenvalue of the matrix J naught is negative and others are not possible to identify. So remaining eigenvalue of the roots follow of the following polynomial function. We completely calculate mathematical calculation. According to the Rubit's criteria, the above equation will give negative roots or roots with negative real part if the following condition satisfied. Hence, the disease-free equilibrium mean naught of the system is locally asymptotically stable when R naught is less than 1. So, locally asymptotically stable endemic equilibrium. So, if when R naught is greater than 1, then the endemic equilibrium E1 is locally asymptotically stable under some restriction of parameters, otherwise unstable. The Jacobian of the system of the endemic equilibrium points. This is Jacobian matrix. Similarly, here we observe one of the eigenvalue is negative, others are not possible to identify immediately. So we convert these things to the polynomial equation. From this polynomial equation with restriction of some parameter, so Rudhurwitz criteria follows that is asymptotically stable. Even we prove global stability of endemic equilibria also by using Lyapunov function. We use this Lyapunov function where W1, W2, W3 are some strictly positive real number allowed to the function L to the positive. So now this is a complete calculation base. The mathematical model put the expose. This value is substitute, and also mathematical model systems satisfy the following relation at the equilibrium point. With consideration of this one, we find out W1 W2's relation, and we consider W1 equal to W2 equal to 1, and finally we got arithmetic mean is greater than equal to the geometric mean. So we can say that this is equal to 0. It holds U1, U2, U3, U5 equal to 1. So S1 equal to S star, we got U1 equal to E star, Q equal to Q star, IA equal to IA star, IS equal to IS star. Hence, from the Lassell's invariant principle, the equilibrium U1 of the given system is globally asymptotically stable. So numerical simulation. For the numerical simulation of the model, we consider all the parameters are per day basis. Following consideration of the set, these all are not, some are assumed data and some are we collect from different model also. So here from we got the reproduction number is less than 1, so 0.2606, and similarly some changes we did some change. Endemic for endemic equilibria, this data we use, we got the reproduction number more than 1, 2.1498. So this is the variation of all compartment performing the stability of disease-free equilibrium R naught is equal to less than 1. Similarly, the variation of all compartment performing the stability of endemic equilibrium point with R naught is, it should be greater than, by mistake it is less than 10. The variation of infected population with time for different values of M we consider. So similarly, we saw variation of different values of gamma 1 with time, gamma 2 also with time, gamma 3 is also shown here. We did sensitivity analysis of the reproduction number. So in the sensitivity analytics, directly we come to the simulation part. So for forward sensitivity analysis of R naught, we saw the lambda is the most sensitive parameter. Next sensitive parameters are beta 1, beta, and mu are the next level sensitive parameters. Similarly, if you see other one, rho 3 and J2 also most sensitive parameter. Okay, now you see in this section we perform sensitivity analysis for the parameter involved the reproduction number R naught, which reflect that increase or decrease in this parameter cases increase or decrease in R naught. It is used to discover a parameter that have a high impact on R naught and should be targeted by the intervention strategies. If such variable is differentiable with respect to the parameter, then sensitivity index is defined use partial derivatives. The normalized forward sensitivity index of R naught, which differentiable with respect to given parameter P. But this above formula can be used to compute the analytical expression of sensitivity of R naught to each parameter that includes other thing I just told. So okay, so correct estimation of this parameter, it is very important to predict the transmission of the disease. Next our model we convert, extend the optimal control model. Since we saw here, this is we saw beta 2 and beta are the sensitive parameter, and rho also one of the sensitive parameter. We introduce in here beta, in here we one of the introduce optimal control. Even beta 2 also we introduce optimal control. Similarly, so we introduce in gamma 3 another one optimal control, and rho 2 also, no, gamma 2 we introduce another optimal control, and rho 3 we use based on sensitivity analysis, whatever more sensitive parameter, there we use the optimal control. So we extended our proposed model optimal control to explore the best cost effective and time dependent control strategy that can be reduce the number of infective in the specific interval of time. Three independent optimal control parameters are U1, U2, U3. If U1, U2, U3 are 0, no effect is placed in this control at time t. If they equal to 1, the maximum effort is applied. So the control variable U1 represent the reduction in the transmission between human to human via using surgical masks, social distancing, self-isolation, sanitization, and awareness of the transmission of the disease. The control variable U2 represent the increase in the testing facility, which can lead the first detection of COVID infected cases and recovery, and add additional time dependent parameter eta 1 U2 in the rate of detection rho 3. The control variable U3 shows that use of effective drugs of transmission treatment measure of the infectious humans. Eta 2 is the modification parameter.
Dr. Naba, sorry
Yeah,
to
please.
interrupt you, but you are running out of time. Please.
Oh,
wind up
sorry,
in
sorry.
1 minute. Yeah.
Okay, just
You have
almost
2
a
more
minute.
minutes.
No, please. No, thank you, madam. This is we study the behavior of the proposed model, use optimal control theory, the objective function. These are complete mathematical theory. So we use Lagrange's here, and we use Pontigray maximum principle, and we use Hamiltonian. So finally, we got the U1, U2, U3's value, and we did the simulation. So Matlab simulation, this is and we some policy we make. Policy 1, employing control intervention U1, employing control intervention U2 and U3, and control intervention U1, U2, U1, U3, and U2, U3s, and employing control intervention U1, U2, U3. This is a control profile of U1 when U2, U3 are 0. This is U2 when U1, U3 are 0. U3, U1, U2 are 0. Similarly, we control intervention with U1 and U2 when U3 is 0, U1 and U3 when U2 is 0, U2 and U3 when U1 is 0, and U1, U2, U3. When you saw the and finally we another one things, variation infected human population against time with and without optimal control. So this red one is without control and green one is the with control. So this is our conclusion. Here a SCIR, a mathematical model of COVID virus, is formulated. So this is free equilibrium, basic reproduction number are not computed. Stability analysis we did locally as well as globally. Sensitivity analysis also we perform here. Numerical simulation perform, and media has a positive impact of equilibrium level. Infected human increase the parameter M, which corresponds to media decrease the equilibrium level of the infected human. We extended this model to optimal control, and numerical simulation performed for the following combination optimal control. Simulation results suggest that optimal control strategy is a very effective in reducing the total number of infection if all three are applied simultaneously. These are our references. Thank you very much.
Thank you, Dr. Naba,
Yeah.
for your talk.
Yeah.
I'm thankful to all the presenters, and Dr.
Yeah.
Naba, Dr. Nabasheshu, and Dr. Dr. Ghoshal for their wonderful presentation. Thank you very much, everyone. Thank you, audience, for listening. Over to Dr. Vamsi.
Thank you all the paper presenters, and also
Thank you.
thank you, Dr. Surabhi, for chairing the session. So we will close the afternoon session now, and evening
Okay.
6 p.m. We will meet sharp for the further proceedings of the conference. I request all the participants who have joined us in the Microsoft Teams to stay on the Teams for next few minutes for a photograph session. Thank you. We'll wind up the live streaming for this session now. Saira. Thank you, Dr. Surabhi.